The first one is sigma, metal chelate affinity chromatography, in which we bind the proteins to the column and then elute with nudazole. And you see now that from 5 mils of lyser, we actually obtained a much smaller volume of purified sample. So technically what we do, we collect fractions and then measure the enzyme activity in each fraction, and then we only take the fractions that show enzyme activity. In this case, the activity was eluted in fraction 2 in a total volume of 0.5 mils. It might be different in the exam. Maybe the activity will be eluted in not one but several fractions, and they might have different activity. But the point is, we start from one volume and then we end up with a different volume of sample, and of course different activity of this volume. The protein content also measured, and the protein content decreases even more dramatically because only a small fraction of the protein molecules in the initial lysate is our enzyme. So as you can see, the protein decreases from 7 milligrams per ml to 0.2 milligrams per milliliter. But this is the concentration. If we are to calculate how the total protein changed, we will see that the change was even more dramatic because the volume decreased as well. So 5 times 7 milligrams is 35 milligrams of protein total. 0.2 multiplied by 0.5 is 0.1 milligrams total. So 350 times decrease in the total protein amount. But of course you don't need to calculate all this in your mind. As I said, you do it in the table, and you'll do it when we get to this point. So the next step of purification was some additional chromatography. So the fraction that contains the enzyme activity was dissolved and loaded on ion exchange column, and after the column was washed to remove the unspecific proteins and contaminants, it was eluted in a salt gradient, and it was found that 3 of the fractions, number 12, 13, and 14, contain the enzyme activity. Those fractions were each 200 microliters, so 0.2 mils. And they were combined because they contain the enzyme. We don't need to work with 3 separate fractions. We pull them together. The total sample becomes 0.6, and when we measure the activity of the enzyme in its combined fraction, it is 20,800 units per milliliter. But again, we don't have a milliliter, we have 0.6 because we combine 3 fractions, 200 microliters each. Alright? So this is very much the first part of the problem. you have all the data that is necessary to calculate the important characteristics of purification, which are the purification yield and the fault of purification. And the second part of the problem will ask you to determine the molecular weight of your protein. So I'll read what it says and then discuss it very briefly. So an aliquot of the combined fraction from the ion exchange was analyzed by SDS polyacrylamide gel electrophoresis. And when the gel was stained, it revealed a single protein bound with a relative mobility of 0.56. This is important, that it's a single protein bound. This allows us to assume that all the protein that is in this sample belongs to our enzyme. If there were multiple bonds and we did not know how much of those multiple bonds is the fraction of your protein, then we could not solve the problem. But because it's a single protein bond, all the I don't know how many micrograms or milligrams of protein in this sample belongs to the enzyme. So when we determine the molecular weight of this enzyme, we will then be able to determine how many micromoles or nanomoles or picomoles of this enzyme are in our sample, because it is purified. There is only protein in the sample. Okay? So you know the relative mobility, and you have to calculate the molecular weight of the protein. You need a calibration curve for this, which is built by using the relative mobilities of proteins with known molecular weight. And that's why we include this ladder in the separation. We spend one lane of the gel to separate a special marker that contains about 10 different proteins with known molecular weight, and you will either get a picture of the gel, and you should be given the size and the molecular weight of the proteins that you should measure those relative mobilities by yourself, or you will be given the relative mobilities themselves. So this is sufficient data to calculate the molecular weight of your protein. So how we now approach this confusing and fairly complex problem? As I said, the key to efficiency is to organize your data into a table, and directly when you calculate the corresponding value, you just write it in the table. So we have this data, the volume of the sample at each particular step of the purification. We have the protein content at each particular step, and we are given the either the activity per milliliter or something like that. But from the data, you should be able to fill all the columns of the table. So how is the table organized? In this example, we have the volume, the protein content, total activity in units. This micromole per min, this is a unit by definition. Then we need to calculate the specific activity of our enzyme. So the specific activity is what's necessary to calculate the values in the two last columns, which are in. So we calculate the total purification and the purification here. And depending on the purification strategy, you will have 1 or 2 or even 3 different steps of purification, but there is always the beginning, the initial state, which is the lysate. So in our case, we have 3 rows for the lysate, for the first step, and for the second step. And we have entered the volumes here, the protein constant, and then we do the calculation of the activity. You're given in the problem the activity in 1 mil, so you have to multiply the activity by the number of milliliters, I think, and you get those numbers. And then the specific activity is the total activity divided by the total protein. So the total activity in units divided by the total protein in milligrams, given here. So the definition of specific activity is units of activity per 1 milligram of protein. So when you enter all these values here, what you immediately see is that the total activity goes down as we purify the protein. This is the second law of thermodynamics. Whatever we do, things get worse. They never get better. This is the law. So our total protein activity always goes down because part of the enzyme gets inactivated. But what goes up very significantly, dramatically, is the specific activity of the protein. We start with 514 units per milligram, and then immediately after the IMAC, it becomes 150,000. Why? Because 2 things combine to result in this huge increase of specific activity. First, the total protein amount drops down dramatically because we get rid of all the contaminating proteins, which are 99.999% of the total protein. And secondly, the volume also decreases, so the specific activity actually goes up very dramatically. So once you calculate the specific activity in this column, it will be very easy to calculate the purification and the fault of purification. Obviously, the fault of purification is 1. For the lysate, there is no purification. So, and the yield is 100% because we didn't yet lose anything. To calculate the fault of purification, you simply divide the specific activity at a particular step by the specific activity of the protein in the lysate of the enzyme. So in this case, 150,000 divided by 514 should give us 292. So